Hey geometry class, in this section 5.4 we're going to be looking at something called medians and altitudes. In the last two sections we have studied a little bit on um, different I'm going to call them centers of triangles. We've looked at angle bisectors and perpendicular bisectors of the sides and angles of triangles and how they all come together to one point inside or outside or on the triangle. But they are those types of lines that you can draw on a triangle end up being concurrent. So for the perpendicular bisector, we end up having the point of concurrency was the circumcenter, and for the angle bisectors, it was the incenter. Now we come to here, this section, the last two types of centers of triangles that we're going to be studying will come from these two things right here, medians of a triangle and altitudes of a triangle. And we'll look at those and what the points of concurrency those have. All right, so the first thing in this section that we're going to be looking at is a median of a triangle. A median of a triangle is a segment whose endpoints are um, a vertex of a triangle and the midpoint of the opposite side. So to draw a median of a triangle, here's just one single median drawn in this triangle. You have three medians, just like you have three angle bisectors and three perpendicular bisectors in a triangle. You're going to have three medians, but the median goes from the vertice of a triangle to the midpoint of the opposite side of that triangle. So find all of your midpoints on each side of your triangle and then connect the vertice to the midpoint of the opposite side of that triangle, and you've got your median. And like I said, every triangle has three medians, and the medians are concurrent. Let's look at their point of concurrency. So the point of concurrency of the medians of a triangle is called the centroid of the triangle. The centroid is always on the inside of the triangle, just like the incenter was always on the inside of the triangle. The centroid is also called the center of gravity because it is the point where the triangle region will balance. And I will show you a little project in class that we'll do together on the center of gravity, the centroid of a triangle. It'll just be a quick project. But here is something called the centroid theorem. The centroid of a triangle is located 2/3 of the distance from each vertex to the midpoint of the opposite side. So like these three state right here, this right here, AP is equal to 2/3 the whole distance of A to Y. So this is 2/3 of the whole median from A to Y. And then same thing goes for the other two medians. You have BP is equal to 2/3 of BZ, and CP is 2/3 of CX. So we'll be looking at some exercises here in a little bit. You can break whenever you know you have P here in the center of your triangle is the centroid. Um, these segments right here can be broken up into thirds. So this is 2/3. So this length right here, PX of this whole length here, CX is actually 1/3 of CX. Okay, so let's look at some exercises. Okay, so in this triangle, before we get started on this exercise, we know that S here is the centroid because we see that it goes, all of these segments that are inside this triangle go from the vertice to the midpoint of the opposite side. See how this marking here is the same as this marking here. Same goes for LR. It goes from the vertice to the midpoint of the opposite side. Same for MP. This goes from the vertice to the midpoint of its opposite side. So this right here is how you can tell that S is the centroid, or the point of concurrency is the centroid. Okay, so let's use our centroid theorem to help us in figuring out what we're asked to find. So triangle LMN, LR is equal to 21 and SQ is equal to 4. So knowing this information up here, let's find what LS is equal to. And LS, let's look at this, is this portion of it right here. LS, remember, from the vertice to the midpoint is equal to 2/3 of the whole median, so LR. So I'm going to write that out. LS is equal to 2/3 of LR. And we know that, well, or RL, you can write it the other way around. Let's do that. Whoops. That's right, RL. Okay, so LS is what we're asked to find, and LS is equal to 2/3 times RL, which is 21. And if you do this calculation, you will see that we have 14 as our answer. So LS is equal to 14. Okay, again, same triangle as the previous exercise. This time, we're going to be using this portion of our information that we're given to help us in finding what NQ is equal to. So SQ is this little distance right here, and NQ is the whole distance. So remember, this is 2/3 of the whole distance, and this right here is 1/3 of the full distance. So you can say that SQ, let's go ahead and write that down, SQ is equal to 1/3 of NQ. We know what SQ is equal to. Let's go ahead and plug that in. SQ is equal to 4. Sorry, having trouble with my little pen. Okay, 4 is equal to 1/3 of NQ. Well, to get rid of 1/3 on this side, let's multiply both sides by 3. And that cancels out 3's here. And we end up with 12 is equal to NQ. And we're done. We found what NQ is equal to. 12. Okay, so let's do another exercise just to see if we're all on the same page with understanding centroids and medians of triangles. So in this next exercise, we are given some information about this triangle. Again, Z is our centroid of our triangle because we can see that all the vertices go to, we draw from the vertice to the midpoint of the opposite sides for all three. We have medians being drawn here. And let's see, we have ZW is equal to 7 and LX is equal to 81. Well, first we're asked to find what is KW. Let's see, KW. Okay, KW is this median right here, and we are given ZW. So ZW right here. All right, so just like the last example, part B, we're going to figure this one out. So remember, WZ, or ZW, let's write it just like that, ZW is equal to 1/3 KW. Or actually, you can do this either way. Solve it like this. 3 times your smaller side length of your median is equal to the whole thing. I kind of like that one better. No fractions. Okay, so plug in what ZW is equal to. ZW is equal to 7. So KW is equal to 21. And there we go. That's what we were looking for. All right, in this exercise here we have, we're going to find LZ from knowing LX is equal to 8.1. So LX, let's find that one. LX is this whole length of our median right here from L to X. And we should know that if we're looking for LZ, which is from the vertex to the centroid, that is 2/3. So LZ is 2/3 of LX. Just following that theorem here and putting in the proper letters. And LX, well, that, whoops, sorry guys. Let's go to the previous slide. LX is equal to 8.1. So LZ is equal to this. So do that calculation and you'll find that it is equal to 5.4. And we're done with that one. All right, so far we've studied several different types of centers of triangles, the centroid, what we just looked at, the incenter and the circumcenter, and how those all come from different types of, like drawing the angle bisectors of a triangle or perpendicular bisectors of all the sides of a triangle or the medians of a triangle. Here we look at one more, something called the altitudes of a triangle, and they are all going to be a concurrent. They all come together at 1.2, a point of concurrency. And altitudes of triangles are a bit more, I think, probably the hardest concept to understand out of all the other centers of triangles. But let's take a look at it here. It says an altitude of a triangle is a perpendicular segment from a vertex to the opposite side or a line containing the opposite side. Every triangle has 3 altitudes, and an altitude can be inside, outside, or on the triangle, just like you see in these 3 triangles. An acute triangle, the point of concurrency is going to be on the inside. And then this right here, the point of concurrency for the obtuse triangle is on the outside. And then for a right triangle, it's going to be on that right angle in the right triangle. Okay, so let's look at these a little bit closer. So the altitude, how the definition goes, let's look at the acute triangle one. So the vertex, here's how you draw an altitude. You go from the vertex, point A here, to the opposite side, but this line must be perpendicular to that opposite side. Okay, so let's look at B here. B here, so the vertex is where you started at, and you draw over to the other side, and it must be perpendicular to this side. Okay, so that's how you draw altitudes. But in some triangles, the altitudes cannot be drawn on the inside of the triangle. So let's look at this one real quick, this obtuse triangle that we have here. So here's our vertex A, and we cannot draw an altitude from vertex A to this opposite side that's going to be perpendicular to it. So we have to extend this line out to be able to draw a line from the vertex A perpendicular to this line, or the line containing this side of a triangle. Okay, so A down, that is our altitude of this triangle right here. From A to D, that is one of our altitudes anyway. And that's how you're going to find the rest of them too for an obtuse triangle. You have to extend these lines out further to help you in finding the altitude of two of the sides of the triangle. The one with the obtuse angle, that vertex to its opposite side, going perpendicular to it, and that line you won't have to extend. That's going to be on that line somewhere. Okay, and the right triangle, you can see how that one's not going to be so bad to find. The altitude, or the point of concurrency of all the altitudes, is always going to be this point right here on the right triangle, or on the right angle of the right triangle. Okay, let's go to the next one. All right, so hold on, let me see. Yep. Okay, so in this triangle right here, QRS, the altitude QY is inside the triangle, just like we saw in the other obtuse triangle that I just showed you. QY is on the inside, but RX and SZ, these two altitudes, are not on the inside. So notice that these lines contain the altitude, are concurrent at P. See, if we extend all these lines out for our obtuse triangle here, we do have a point of concurrency, and all these points of concurrency where the altitudes meet is called the orthocenter of the triangle. So let's go back here. These points of concurrency, those are called the altitudes, or sorry, the orthocenters. Now there is an interactive website I wanted to mention to you about these altitudes of triangles that we can go to. This thing right here, I think will help you in visualizing the altitudes of triangles a little bit better if you just go to this website and play around a little bit with the manipulative software that they have there. All right, so the last thing I have for you here is the lesson quiz. It's all about centroids of triangles and using that centroid theorem that we looked at, and finding links using that theorem. So solve these 3 problems and we will go over them in class when we get back to class. And I will see you later. Goodbye, everybody.